Tonight, we're going to look at something that sounds wild and hard to believe, but may be one of the strangest ideas in all of science. The idea that we might be living inside a black hole. You've probably heard of black holes many times before. Scientists talk about them often when they speak about space. But here's what most people don't stop to think about. Some researchers now suggest that our entire universe could exist inside one of these objects. When you really try to understand what that means, when you slowly picture space folding in on itself, it changes how you see reality itself. This is not just a bold claim or a strange thought. It's an idea so deep that it pushes the limits of what the human mind can hold. And by the end of this journey, you're going to understand why scientists even consider this possibility and why it hasn't been ruled out. Before we go any further, if you enjoy deep and careful explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a big difference for this work. Now, let's begin. The idea is unsettling. Every star, every galaxy, every speck of matter we can see might be part of something far stranger than the empty space we imagine. We think of the universe as infinite, stretching beyond our sight, a vast expanse without borders. Light travels, planets orbit, galaxies drift apart. But what if this sense of openness is an illusion? What if the universe is not open at all, but folded inward, shaped and contained by forces we barely understand? Black holes are often seen as endpoints, places where matter disappears, swallowed by gravity so intense that not even light can escape. They are regions of finality, singularities, points of infinite density where the known laws of physics break down. And yet, recent scientific explorations suggest a different view. A black hole is not only a consumer, it is a container, a region of space where extreme gravity bends everything, creating boundaries, curving paths, shaping the behavior of matter and light. In this view, a black hole does not simply end space, it holds it. The mathematics of general relativity describe this clearly. Space can curve, stretch, fold. Time can slow, speed, or twist. Inside a black hole, these effects are extreme, but they follow precise rules. The same rules that govern the cosmos. Now imagine scaling this to the size of the universe. What if the universe itself is the interior of a black hole far larger than anything we can measure? A single singularity at the core, bending all of existence around it. The consequences are profound. Our understanding of distance, time, and motion would be incomplete. The cosmic background radiation, the afterglow of the Big Bang, might be influenced by the boundaries of this invisible container. The expansion of galaxies, the flow of cosmic energy, the large-scale structure of the universe, all could be shaped by the limits imposed by gravity. This is not science fiction. Equations derived from Einstein's field theory allow for the possibility. Certain solutions suggest that a black hole, when scaled, could produce an interior space with properties remarkably similar to our observed universe. The curvature of space, the relationship between energy and expansion, even the formation of cosmic structures could match what we see if we are inside such a region. It is a radical claim, one that challenges centuries of assumptions. The universe is not merely large, it is constrained. It may be finite, yet appear infinite from within. That idea forces a different perspective on the nature of reality. For most of human history, the night sky has inspired wonder. People imagined limitless space, endless journeys across the stars. Modern astronomy seemed to confirm this. Hubble telescopes and space probes measure distances across billions of light years. Yet, all of these observations are still inside a boundary we cannot cross. The edge, if it exists, is hidden behind gravitational horizons we cannot detect directly. Scientists begin to ask, what are the limits of our universe? What shapes the space in which light moves? What rules determine the flow of time itself? When we look outward, the distances appear infinite. Light from distant galaxies takes billions of years to reach us. We measure the expansion rate. We map clusters of galaxies. Yet, these observations could be influenced by a larger structure, a space that curves back on itself, shaped like the interior of a black hole. The strange and uncomfortable truth is that being inside a black hole would not feel like falling. Locally, space could appear normal. Galaxies would move, stars would shine, planets would orbit. Physics would function as usual. The curvature and boundaries only become noticeable on the grandest scales, beyond what any human could directly perceive. And the very tools we use to measure the universe, the speed of light, the way gravity bends space, the flow of cosmic energy, could all be part of the rules set by this interior. The universe could be simultaneously vast and contained. Every observation we make, every map we create, might trace the outline of a hidden structure. This idea reframes the meaning of infinity. If the universe has an interior horizon, it may be finite, yet boundless in perception, a space that curves in ways our intuition cannot grasp. Time, too, could be affected. Near the edges of a black hole, time slows relative to distant observers. Scale this up, and the history of the universe, from the formation of stars to the present, may unfold within a time framework shaped by the black hole itself. We assume that the universe began with a big bang, that the cosmos expanded outward from a singular origin. But if the universe is inside a black hole, the Big Bang could be the natural unfolding of matter and energy within a larger gravitational container. The laws of physics would still apply, but the context would change. Expansion might not be unlimited. Growth might be curved by an invisible boundary. The more scientists explore these models, the more they realize how conventional assumptions may be incomplete. We take for granted that space extends without limits. We assume that gravity shapes stars and planets, but not the universe itself. We think light travels in straight lines, but within a black hole interior, straight lines curve in ways our eyes cannot see. The idea provokes discomfort. Our cosmic maps, our charts of galaxies, our measurements of cosmic expansion, all might be pieces of a larger hidden picture. What we call empty space may be shaped, contained, and curved. The universe might be an interior, rather than an exterior, structure. It is a humbling concept, one that places humanity within a context far beyond ordinary imagination. It invites questions about the nature of reality itself. What if everything we know, the stars, the planets, the galaxies, the very flow of time, is a small part of a space shaped by forces so extreme we cannot see them? If we are inside a black hole, the rules we observe locally may not reveal the full truth of the cosmos. And the ultimate question remains: if the universe is contained in this way, how do we detect the edges, and what do they tell us about the very nature of existence? Black holes are not just holes. They are points in space where gravity becomes extreme. Matter collapses into a single location, compressed beyond what we can normally imagine. At the center lies the singularity, a point where density grows infinitely large and the known laws of physics no longer hold in the ways we understand. Around the singularity lies the event horizon, a boundary that marks the point of no return. Cross it, and escape becomes impossible, not because of walls or barriers, but because gravity curves space and time so intensely that all paths lead inward. Light itself bends or stops, unable to move outward. The space near a black hole is strange. Time slows as you approach the event horizon. A clock near the edge ticks more slowly than one far away. This effect, known as time dilation, is not science fiction. It is predicted by Einstein's general theory of relativity and observed in weaker forms near massive bodies like Earth. Near a black hole, the effect is extreme. A few minutes for someone near the edge could equal years for someone far away. Space itself stretches and warps. Straight lines are no longer straight. A path that appears direct from a distance curves inward as gravity pulls everything toward the singularity. The stronger the gravity, the more extreme the curvature. Objects falling into a black hole do not fall in the usual sense. They follow the curvature of space-time, moving along paths determined by the intense gravitational field. The experience is counterintuitive. Locally, an object might feel normal, floating in free fall. But measured from the outside, its motion appears slowed, elongated, and distorted. Black holes form from gravitational collapse. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. Its core contracts rapidly, matter compressing into an increasingly small volume. If the core is massive enough, nothing can stop the collapse, and a black hole forms. These objects vary in size. Stellar black holes form from individual stars. Their mass may be a few times that of the Sun, compressed into a volume the size of a city. Supermassive black holes found at the centers of galaxies hold billions of times the mass of the Sun. They shape the motion of stars, influence galaxy formation, and dominate the structure of their surroundings. Despite their density, black holes are not always obvious. They are invisible because light cannot escape. We detect them indirectly. Nearby matter falling into a black hole heats up and emits radiation, often in X-rays. Stars orbiting an unseen mass reveal its presence. Gravitational waves, ripples in space-time from colliding black holes, allow scientists to observe these extreme events across the cosmos. The mathematics of black holes is precise, yet strange. The Schwarzschild solution describes a non-rotating black hole, a simple model capturing the core ideas. The Kerr solution adds rotation, showing how spin affects the structure of space around the singularity. Rotating black holes drag space around them, twisting the paths of matter and light. Inside these models, space and time behave in ways that challenge our intuition. An observer near the event horizon sees the outside universe change. Distant events appear accelerated. Time and space are intertwined, forming a single fabric that stretches, compresses, and folds under the weight of gravity. Black holes are not only extreme in density, but in effect. They are laboratories of physics, where quantum mechanics and general relativity meet, sometimes clashing in paradoxes, yet guiding new understanding. These extreme properties provide a foundation for imagining a universe-scale black hole. If a black hole can contain a region of space with its own geometry, if it can shape the flow of time and bend the paths of matter and light, then a larger version could contain an entire cosmos. Scaling the principles of singularities and event horizons does not change the rules, it extends them. Gravity still curves space, time still flows along paths influenced by mass, and matter still obeys physical laws. The difference is scale. What is small and invisible in a stellar black hole becomes vast and cosmic in a supermassive or universe-scale structure. Scientists explore these models using equations derived from Einstein's theory. Solutions suggest that a black hole can create an interior space with properties remarkably similar to what we observe in our universe. The curvature of space, the expansion of energy, even the formation of structures could match known patterns. The event horizon, while a boundary, may not be a wall, but a smooth edge of a larger contained space. Observers inside would not detect the curvature in everyday experience. Stars would shine, galaxies would drift, and light would travel. The extreme bending of space-time becomes noticeable only at the largest scales. Time dilation would shape cosmic history subtly, influencing the development of stars and galaxies without any obvious local effect. Understanding black holes prepares us to consider the possibility of our universe as a similar structure. The extreme gravity, the singularity, the event horizon all serve as a model. By studying smaller, observable black holes, scientists gain insights into how a larger, universe-scale black hole might behave. Observations of supermassive black holes at galactic centers, gravitational lensing of distant light, and the echoes of gravitational waves all provide data. These clues hint at the way extreme gravity organizes space and time, giving shape to what seems limitless. The paradoxes of black holes, the information problem, the warping of time, the bending of light, highlight the depth of what is possible. They show that our understanding of space is limited by perspective. From inside a black hole, the universe might appear normal. Locally, physics operates as usual. Only on scales beyond ordinary observation would the extreme structure become apparent. By examining these objects, scientists can hypothesize about structures larger than galaxies, larger than clusters of galaxies, structures that could, in theory, hold an entire universe. The study of black holes also reveals that space is flexible. It is not a fixed backdrop, but a dynamic medium shaped by mass and energy. Stretch it, compress it, curve it. Space adapts. Time responds to these changes, flowing differently depending on location and motion. Understanding this flexibility is key to imagining a cosmos that behaves like the interior of a black hole. We learn that boundaries may exist without visible edges. Limits may define the behavior of matter without obvious walls. Horizons may mark regions of inaccessibility while remaining invisible in practice. These lessons prepare the mind to consider the universe as a contained space, shaped, curved, and bounded by forces that are extreme, yet consistent with known physics. In this way, the study of black holes becomes more than curiosity. It becomes a model for thinking about the cosmos, a framework for exploring ideas that stretch human understanding, and a guide to imagining the universe not as endless emptiness, but as a space shaped and held by gravity itself. Gravity is the force that binds the universe together. It pulls, it shapes, it defines the structure of space. In black holes, gravity reaches extremes we rarely encounter elsewhere. Mass becomes concentrated in a very small space, so dense that normal ideas about volume lose meaning. The amount of matter packed into the singularity is enormous, yet the region around it remains tiny by cosmic standards. Density is the key. The higher it rises, the stronger gravity becomes, curving space around it in ways that defy simple understanding. Gravity is no longer a gentle pull. It becomes a sculptor, bending space and time, forcing paths of matter and light to follow curved trajectories. In ordinary settings, gravity is weak. Planets orbit stars, stars orbit galactic centers, and space seems mostly empty. But in a black hole, the concentration of mass creates curvature so extreme that local geometry changes. Straight lines bend, volumes warp, distances expand and contract in ways that challenge intuition. This geometry is not random. It follows precise rules, expressed through equations derived from Einstein's general relativity. These equations describe how mass and energy dictate the shape of space and the flow of time. They predict the presence of singularities, event horizons, and the warping that defines black holes. Scientists have extended these principles to imagine what the inside of a black hole could be like. Internal geometry, the shape of space within the boundary, can vary depending on mass, rotation, and energy content. Models suggest that a black hole can contain a region where space is finite but unbounded. Curvature closes back on itself. Paths that seem straight eventually loop. Light may travel in circles. These features imply a contained space that, from the inside, may appear vast and regular, even while it is finite in total volume. Some solutions to the equations show that a black hole can create an interior resembling a small universe. Expansion may occur naturally within the curved space. Matter can distribute in ways consistent with observations of cosmic structures, and the flow of time follows predictable rules shaped by the internal geometry. These ideas are mathematically rigorous. They arise not from speculation, but from careful analysis of Einstein's equations under extreme conditions. Researchers have studied different types of black holes, rotating, charged or non-rotating, and modeled their interiors. Each scenario provides insights into how a large contained region of space behaves. The concept of a universe inside a black hole is supported by these models. If gravity can contain space and matter on a stellar scale, nothing in the equations forbids the same principle at larger scales. Mass, density, and energy define curvature. Curvature defines geometry. Geometry shapes how matter and light move. There is a chain of cause and effect. In this framework, boundaries exist without walls. Horizons mark limits that cannot be crossed, but they do not act like barriers. Space curves inward, creating a finite but seemingly unbounded region. Time follows paths determined by the curvature. Matter moves along trajectories set by geometry. Even the formation of galaxies and large-scale structures can be influenced by the internal shape of space. Simulations demonstrate that these principles produce environments compatible with what we observe in our universe. Cosmic microwave background patterns, the distribution of galaxies, and rates of expansion can all be modeled within a contained, curved space. Researchers use both analytical solutions and numerical simulations to explore these scenarios. Complex equations are solved with computers, revealing how density gradients, rotation, and energy distributions affect internal dynamics. Some models show expansion from a central region outward, resembling a Big Bang within a confined space. Others suggest rotational effects can stabilize structures, allowing matter to settle into organized forms. The physics is demanding, yet the results are consistent. Black holes are not simply voids, They are structured regions where extreme gravity creates predictable behavior. Understanding these behaviors on smaller scales informs hypotheses about larger, universe-sized black holes. The interplay between mass, density, and gravity produces emergent patterns. Event horizons mark boundaries, but inside, space can support the formation of complex structures. Paths of light curve, time flows according to the internal geometry, and energy spreads in ways that can mimic the expansion observed in our universe. The containment does not limit the richness of physical phenomena. Stars can form, planets can orbit, and cosmic events unfold, all within the rules set by the geometry. Mathematically, a black hole acts as a cosmic container. The interior is not empty. It is full of potential structured by the curvature of spacetime. Researchers continue to investigate how these models apply to the real universe. Observations of black holes, combined with theoretical analysis, test the limits of these ideas. The equations allow for solutions where an interior can grow, expand, and evolve without violating known laws of physics. These models remain active areas of study. Scientists debate how properties like rotation, charge, or quantum effects modify the interior. Hawking radiation, the information paradox, and quantum gravity introduce additional layers of complexity, but the underlying structure remains grounded in relativity. The concept of a universe contained in a black hole emerges naturally from this framework. It is not a story, a metaphor, or an abstraction. It is a prediction based on the way mass, density, and gravity interact under extreme conditions. Each step is supported by calculation, observation, or rigorous simulation. The interior of a black hole is a laboratory of physics, revealing how space itself responds to matter and energy. Its geometry governs the behavior of everything within. Patterns form, paths bend, time flows, and structures evolve according to predictable laws. Scaling these results suggests that a universe-scale black hole could produce an internal space consistent with our observations, a region where matter forms galaxies, light travels, and time unfolds. The boundaries are invisible, but they exist. Horizons define the limits. Inside, physics operates normally, yet on the largest scales, the structure shapes the behavior of the cosmos. This perspective transforms our understanding of containment. A black hole is not just an object. It is a space, a framework, a model for how gravity defines regions. It is both empty and full, simple and complex, finite yet vast from the inside. The interplay of mass, density, and geometry demonstrates that space can hold itself together, curved and defined, supporting the flow of energy, matter, and light. This knowledge prepares the mind to consider the universe itself as potentially contained. The equations, the models, the simulations all point to the possibility that our cosmos could be an interior, a space shaped by forces of gravity on scales far beyond direct observation. Containment is not confinement in a familiar sense. It is a shaping of reality itself, a definition of the possible paths of space and time, matter and light. Understanding this physics is the first step toward imagining a universe inside a black hole without stepping into speculation. Every line of the equations, every simulation, every observation of smaller black holes builds toward this idea. The universe may be finite, curved, and contained, and yet, from inside, appear limitless. Gravity, density, and mass define the container. Geometry shapes the interior. Time flows according to these rules. And the cosmos, in all its vastness, is the product of the interplay between these fundamental forces. Observations of the cosmos provide a window into the large-scale structure of the universe. Light from distant stars, the distribution of galaxies, and the faint glow of ancient radiation all carry clues about the nature of space. The cosmic microwave background, for example, is a remnant of the early universe. It is the faint, uniform radiation left over from the first moments after the Big Bang. Scientists study its patterns, slight variations in temperature and intensity, to understand how the universe has evolved. These patterns are not random. Tiny fluctuations reveal the density of matter, the formation of early structures, and the expansion history of space. Anomalies in this background radiation have puzzled researchers. Some regions are slightly hotter or colder than expected. Some alignments appear to suggest a preferred direction in space. Others hint at large-scale structures that stretch across distances where random chance seems unlikely. These irregularities, while subtle, provide evidence that the universe may have underlying constraints. The way light has traveled from distant galaxies to Earth is influenced by the shape of space. If the universe is curved or contained, as in the interior of a black hole, light paths would bend accordingly. Scientists measure redshifts to determine how fast galaxies move away from us. On large scales, these motions are surprisingly uniform. The expansion seems to follow rules consistent with a space that is finite yet unbounded. Supernovae, exploding stars used as standard candles, help map distances and measure expansion rates. Their observed brightness and redshift provide precise data on how fast the universe grows over time. When combined with cosmic microwave background studies, the results suggest a universe with geometry that is nearly flat yet subtly curved. This curvature could be explained by containment. If space is folded inward, forming a finite region shaped by extreme gravity, light and matter would still behave as if they are moving through an expansive universe. The limits imposed by a black hole's internal geometry may influence these measurements. Scientists cannot observe the boundary directly. We cannot travel beyond the edge of the universe, nor see past the event horizon of a cosmic container. Instead, they infer structure indirectly. The shape, distribution, and motion of galaxies act as tracers. Gravitational lensing, the bending of light by massive objects, reveals mass concentrations and curvature. Patterns in lensing maps hint at the overall geometry of space. Large-scale surveys map billions of galaxies, charting the cosmic web. Clusters, filaments, and voids form a network shaped by gravity. Simulations show that similar patterns arise naturally in a space constrained by internal curvature, like the interior of a black hole. Even subtle deviations in cosmic expansion rates can provide insight. Some regions expand slightly faster or slower, suggesting that the universe may not be perfectly uniform at the largest scales. These deviations are small, yet detectable with precise instruments. They inform scientists about the possible shape of space, the distribution of mass, and the presence of boundaries that are not immediately visible. The Hubble Space Telescope, the Planck satellite, and ground-based observatories all contribute data. Measurements of light from distant quasars, the distribution of intergalactic gas, and the motions of galaxy clusters all feed into models of cosmic geometry. Each observation acts like a piece of a puzzle. By analyzing how matter and light behave, scientists test whether the universe is infinite or contained. The results so far do not contradict the possibility of a black hole-like interior. Some patterns are difficult to explain under a purely open universe scenario. Anomalies in the cosmic microwave background, alignments of large-scale structures, and slight irregularities in expansion suggest that containment could be a factor. Observations of supermassive black holes at galactic centers also provide hints. Their influence extends over thousands of light-years, affecting star motion and gas flow. If the universe is similar in principle, a single cosmic-scale black hole could exert subtle effects across the cosmos, consistent with observed large-scale uniformity and curvature. Scientists also study the distribution of dark matter and dark energy. These invisible components shape the universe on scales far beyond ordinary observation. Their effects on gravitational lensing, galaxy motion, and cosmic expansion can be modeled mathematically. The results suggest that a contained, curved space can replicate many features we see. Cosmic voids, regions nearly empty of galaxies, might correspond to areas shaped by curvature and gravitational dynamics. Filaments of galaxies could trace the paths of matter along curved spacetime. The universe behaves as though it is both vast and contained. Observational evidence alone cannot prove that we are inside a black hole, but it allows constraints. Patterns, alignments, and structures provide clues about geometry and expansion. Scientists combine these with theory to develop consistent models. Every new observation refines understanding. As instruments improve, faint effects become measurable. Subtle deviations in light paths, small shifts in cosmic microwave background temperature, and precise measurements of galaxy clustering all contribute to a picture of large-scale structure. The emerging patterns hint at limits and curvature consistent with a contained space. Even without seeing a horizon or singularity, the data allows scientists to infer possibilities. Each galaxy, each star cluster, each photon acts as a probe, moving along paths shaped by unseen boundaries. Observations of gravitational waves, ripples in space-time from massive collisions, offer further insight. These waves travel vast distances, their motion influenced by the geometry of space. Analysis of arrival times, amplitudes, and distortions informs scientists about the curvature and expansion history of the universe. Consistency across multiple datasets strengthens the case. Cosmic microwave background patterns, supernova measurements, galaxy surveys, and gravitational waves all converge on a model that can be interpreted as a contained, curved universe. The evidence is subtle but coherent. Scientists do not claim certainty. They report patterns, anomalies, and consistencies. Yet these point toward a possibility that matches the predictions of black hole interior models. Even anomalies that seem random may reflect larger-scale structure, hidden curvature, or boundaries beyond direct observation. Observational science is cautious. Hypotheses are tested rigorously, models are compared with data, and predictions are evaluated. The universe offers no simple confirmation, but it provides clues. By piecing together light, motion, and radiation across billions of light-years, scientists glimpse the shape of the cosmos. Each measurement acts as a guide, revealing how gravity, mass, and energy influence space. Every photon carries a record of curvature, expansion, and flow. Together, they suggest a universe that is not entirely free and infinite, but structured and potentially contained. While we cannot see the edges, we can trace their effects. The patterns of cosmic expansion, the variations in radiation, the motions of galaxies, all hint at limits, boundaries, and curvature. Observations alone cannot settle the question, yet they provide a foundation. They show that a universe shaped by extreme gravity is consistent with what we measure. The cosmos may be far stranger than it seems, shaped not only by matter and energy, but by the geometry of space itself. And as scientists continue to collect data, each new piece of information helps reveal whether the universe is open and endless, or finite, curved and contained, like the interior of a black hole. Einstein's theory of general relativity is the foundation for understanding black holes. It describes how mass and energy influence the shape of space and the flow of time. Gravity is no longer a simple pull. It is a curvature of space-time itself. Massive objects bend space, guiding the motion of matter and light along curved paths. Black holes are the most extreme demonstration of this curvature. The equations of general relativity, solved under conditions of extreme mass and density, predict singularities and event horizons. The simplest solution, known as the Schwarzschild metric, describes a non-rotating black hole. It maps the relationship between distance, mass, and time near a singularity. The Schwarzschild solution shows that within a black hole, space and time switch roles in surprising ways. The radial direction points toward the singularity as time flows, and no path leads outward beyond the event horizon. For a rotating black hole, the Kerr metric provides a more complex model. Rotation twists space, creating frame dragging, where space-time itself rotates around the singularity. This effect alters trajectories of matter and light. In both cases, the interior geometry allows for regions that could, in principle, support a finite but unbounded space. Equations derived from these metrics suggest that the interior of a black hole is more than a void. It is a structured region with predictable rules. The paths of light, the flow of time, and the distribution of matter are governed by the curvature of space-time. Mathematicians and physicists have extended these solutions to explore the possibility of universe-scale black holes. Scaling the mass and radius in the equations produces internal regions with properties similar to what we observe in our universe. Space can be curved, time flows consistently, and expansion occurs naturally from the central region outward. Recent theoretical papers explore this scenario in detail. Researchers examine whether the observed cosmic expansion, the cosmic microwave background, and the formation of large-scale structures can be reproduced within a contained black hole-like interior. These studies combine analytical solutions with numerical simulations, testing the limits of the equations under extreme conditions. Results show that a black hole interior can, under certain parameters, mimic many features of our universe. Expansion, structure formation, and the flow of time remain consistent with known physics. Theoretical support for this model arises from the way general relativity permits curved, finite spaces. While standard cosmology often assumes an open or flat universe extending indefinitely, black hole interior models propose a contained cosmos. The equations allow for a finite volume where boundaries exist in a curved form rather than as hard walls. Horizons define limits, but inside, space can support complex structures. Comparing standard cosmology with these new interpretations highlights differences in perspective. The Big Bang model describes the universe as originating from a singularity, expanding outward. The black hole interior model interprets this expansion as unfolding within a pre-existing curved space shaped by extreme gravity. Observations are compatible with both approaches, but the latter provides a framework that naturally contains the universe within boundaries determined by gravitational rules. This does not contradict known physics. It extends the implications of general relativity. The Schwarzschild and Kerr metrics demonstrate that extreme mass can generate finite, curved space with consistent behavior. By extrapolating these principles, theorists explore whether the universe could behave similarly on cosmic scales. Other solutions, such as charged black holes or more complex rotating models, introduce additional factors. But the central idea remains. The equations allow for contained interiors that support matter, light, and expansion. These models also address questions about the apparent uniformity of the universe. A finite, curved interior naturally explains why the cosmic microwave background appears isotropic, why galaxy distributions follow specific patterns, and why expansion occurs at measurable rates. Containment provides a context in which these features emerge naturally from the curvature of space. Researchers examine the compatibility with quantum considerations, though full unification remains unresolved. The focus here is on classical general relativity and the geometric possibilities it provides. Within this framework, black hole interiors are mathematically consistent regions capable of supporting a universe-like environment. Standard cosmology assumes a simple, mostly flat or slightly curved universe, with boundaries at infinity. The black hole interior interpretation challenges this assumption, proposing that space may be finite yet unbounded, limited yet vast in perception. This perspective arises directly from the mathematics, not from speculation. It is a natural extension of solutions already tested for stellar and supermassive black holes. The equations predict horizons, singularities, and internal curvature, and they allow scaling up to larger, more massive regions. In this light, the universe may not be an infinite open expanse, but a contained region shaped by gravity. Theoretical papers explore variations on this theme. Some examine non-rotating models, others include spin or charge. Each study tests how matter, light, and energy behave in extreme curvature. The results remain consistent with observed features of the cosmos. Horizons mark boundaries, singularities anchor the geometry, and the interior supports the evolution of matter and structure. Mathematics provides the bridge between observable phenomena and possible explanations. While direct observation of a universe-scale black hole is impossible, the equations offer insight. They show that nothing in fundamental physics forbids a contained universe. Instead, they reveal that extreme gravity can shape space in ways that accommodate expansion, structure, and the flow of time. This perspective reframes our understanding of scale and containment. Standard cosmology assumes the universe extends indefinitely. Black hole interior models suggest it may extend only as far as the curvature allows, yet appear limitless from within. Observations, when interpreted through the lens of general relativity, are consistent with both views. The difference lies in interpretation. Mathematicians use the Schwarzschild and Kerr metrics, extended to cosmic scales, to test the plausibility of containment. Simulations verify that a contained interior can reproduce features like the large-scale structure, cosmic microwave background patterns, and expansion rates. Theoretical support is not mere speculation. It arises from equations that have been confirmed at smaller scales and applied rigorously to larger scenarios. Gravity defines geometry. Geometry defines the behavior of matter and light. This chain of causality is well understood in general relativity. Scaling it up to a universe inside a black hole is a logical extension. The mathematics allows it. The models are internally consistent. Predictions match many features of our observed universe. Horizons mark boundaries, curvature shapes the interior, and expansion unfolds naturally. Comparing these models to standard cosmology highlights the radical difference in perspective. Both explain observations, but the black hole interior framework emphasizes containment, curvature, and the role of extreme gravity in shaping space itself. The theoretical foundation rests on solid equations, tested solutions, and simulations that reproduce observable phenomena. It opens the possibility that the universe, as we know it, may be a contained space, a vast interior within a larger gravitational structure. Einstein's equations, Schwarzschild and Kerr metrics, and modern computational studies together provide a rigorous basis. The universe inside a black hole is not fantasy. It is a mathematical possibility, consistent with physics, constrained by observation, and worthy of continued exploration. Time is not absolute. It flows differently depending on gravity. Near a massive object, time slows relative to a distant observer. This is not a theory. It is measured on Earth. Clocks at different altitudes tick at slightly different rates. Around a black hole, the effect is extreme. Near the event horizon, time appears to nearly stop from the perspective of a distant observer. An object falling toward the singularity seems to freeze, stretched across moments, while locally it moves normally. This stretching of time changes the meaning of causality. Events near a black hole unfold along a different rhythm than events far away. Cause and effect still operate, but the passage of time is relative. Light, matter, and energy follow paths defined by space-time curvature. Inside the event horizon, time and space behave differently. The radial direction becomes temporal, guiding all motion toward the singularity. Escape is impossible, not because of a barrier, but because the very dimension of time points inward. The universe itself, if contained within a black hole, would experience time according to this internal geometry. Locally, time might feel ordinary. Stars form, planets orbit, and galaxies drift as expected. Yet, on the largest scales, the flow of time could be shaped by the curvature and boundaries of the space. Expansion is influenced as well. The observed cosmic expansion, the movement of galaxies away from one another, can be interpreted through the lens of space-time curvature. Within a contained space, expansion may occur naturally along the curvature, producing effects similar to what we see. Light traveling across vast distances follows curved paths. Observers inside measure distances and velocities according to local rules. Causality operates, but it is embedded within a geometry shaped by extreme gravity. The arrow of time, the direction from past to future, remains intact locally. Thermodynamics and entropy proceed normally. Heat flows, stars age, and systems evolve. But the overall rate of change across the universe may be influenced by large-scale curvature. Regions far apart could experience relative differences in perceived time due to gravitational effects on cosmic scales. The concept of beyond the event horizon becomes relevant here. While we cannot observe past an event horizon directly, the mathematics predicts how space and time behave internally. All matter moves inward along defined paths. light cannot escape. Time and space switch roles in orientation. Within a contained universe-scale black hole, the interior may have no visible edge, but its structure would influence the flow of events. Causality remains consistent. Events follow predictable sequences. Energy transfers, orbital motions, and stellar evolution all obey the laws of physics. Yet the global geometry imposes constraints that would be invisible to local observation. The expansion of the universe, if interpreted as motion inside a curved, finite space, aligns with these effects. Galaxies move apart, yet their motion is shaped by the overall curvature and boundaries of the space they inhabit. Light curves, distances stretch, and horizons form naturally from the geometry. Time near the center may differ slightly from time at the periphery, producing effects that accumulate over billions of years. Observers inside would not notice small local differences, but the combined effect across the cosmos becomes significant. Scientists use general relativity to calculate these flows. Equations describe how time dilates, how paths bend, and how expansion proceeds under extreme curvature. The results show that a contained interior can support a consistent arrow of time while shaping large-scale dynamics. Gravitational time dilation ensures that the closer to a singularity, the slower time passes relative to distant regions. Expansion can proceed along spatial dimensions, while the flow of local time remains coherent. These principles explain why stars age, galaxies evolve, and the cosmic microwave background develops patterns over billions of years. Light from distant objects still carries information about past events, even when space is curved. Paths are longer, motions are influenced, but signals reach observers in predictable ways. Event horizons define limits. They mark points beyond which escape is impossible, yet within those boundaries, physics operates normally. Structures form, energy moves, and time unfolds according to local geometry. The implications for cosmic observation are profound. We may perceive a universe that seems unbounded and uniform, while the underlying structure is contained and curved. Patterns in cosmic radiation, galaxy clustering, and expansion rates may reflect this geometry. Observers see a coherent cosmos, yet the overall shape and flow of time are influenced by containment. The arrow of time continues to guide evolution, but the global rate of change is shaped by large-scale curvature. Regions separated by billions of light-years may experience effective differences in time, producing subtle but measurable effects. Light emitted from distant galaxies carries information about this curvature, revealing paths shaped by the interior geometry. Gravitational lensing, redshift, and cosmic microwave background measurements all provide data that can be interpreted through these principles. While we cannot look beyond an event horizon, we can understand its influence. Boundaries exist in geometry, not as walls, but as limits to motion. Matter and light follow the paths dictated by space-time curvature. Causality remains intact, but the global structure constrains how events unfold across the cosmos. The expansion of space, the movement of galaxies, and the flow of time are all interconnected. Each is shaped by the distribution of mass, the density of energy, and the geometry of space-time. Inside a black hole, or inside a universe-scale analog, these factors combine to produce a consistent, observable cosmos. Entropy increases, stars evolve, galaxies rotate, yet the large-scale flow of time and space reflects the underlying curvature. Scientists model these effects with precise equations, simulating billions of years of cosmic evolution. The results show that containment does not disrupt physics. Instead, it provides a framework for understanding observed phenomena. Expansion occurs naturally, causality is preserved, and time flows consistently within the geometry. Even extreme conditions near a singularity follow predictable patterns. These calculations allow researchers to explore what a universe inside a black hole would be like without leaving the bounds of factual science. Every photon, every orbiting star, and every region of cosmic radiation fits into this model. Horizons are invisible, but present. Curvature defines limits. Time flows differently depending on location, yet remains coherent locally. Expansion occurs along the geometry. Observers see a universe that functions normally, while the underlying structure remains hidden. This perspective reframes the understanding of space and time. The cosmos may appear infinite and uniform, but the interior geometry dictates behavior on the largest scales. Gravity, mass, and energy shape paths, distances, and durations. The arrow of time continues, guided by entropy and local processes, while global flow is influenced by the curvature imposed by containment. Scientists continue to study these effects, refining models, testing predictions, and analyzing observational data. The interplay between geometry and time offers a framework for understanding cosmic evolution, expansion, and causality within a potentially contained space. And while we cannot cross a horizon or see the singularity directly, its influence is measurable, encoded in the motion of galaxies, the distribution of radiation, and the flow of light across billions of years. Beyond the event horizon, physics continues, governed by curvature and mass. Space and time unfold, matter moves, and light travels along predictable paths. This understanding bridges observation, theory, and mathematical models, allowing scientists to explore the implications of a universe shaped by extreme gravity. The cosmos remains coherent, predictable, and structured, yet the underlying containment challenges conventional intuition about infinite, unbounded space. Our perception of time and expansion is guided by the geometry of the interior. Observers see a universe that functions normally, yet is subtly constrained by the rules that govern black holes, offering a new lens through which to understand the flow of space and time across the cosmos. Black holes are not only massive objects, they are also arenas where quantum physics and gravity intersect. The laws of general relativity describe gravity and the curvature of space, but quantum mechanics governs the behavior of the very small. Near the singularity, these realms converge. The density is extreme, space is highly curved, and quantum effects cannot be ignored. Stephen Hawking's work revealed that black holes are not completely black. Quantum fluctuations near the event horizon produce radiation. Particle-antiparticle pairs form. One falls into the black hole, the other escapes. This emission, called Hawking radiation, slowly reduces the black hole's mass. Over immense timescales, a black hole could evaporate entirely. The discovery of Hawking radiation was a landmark in physics. It connected quantum mechanics, thermodynamics, and general relativity in a single framework. Black holes have temperature, entropy, and energy, just like ordinary physical systems. The entropy of a black hole is proportional to the area of its event horizon. This relationship is unique. In normal systems, entropy scales with volume, but for black holes, the boundary defines it. This hints at the deep connection between information, geometry, and physics. Quantum mechanics also introduces uncertainty. Position and momentum cannot be known simultaneously with absolute precision. Near a singularity, these uncertainties become extreme. Matter and energy fluctuate, and even space-time itself may have quantum behavior. Scientists use semi-classical approaches to study these effects, combining general relativity with quantum field theory. The results are complex, but reveal patterns. Hawking radiation carries information in subtle ways. Whether the black hole loses information permanently or preserves it remains a debated question. This is the information paradox. If a black hole evaporates completely, what happens to the matter and energy that fell inside? Does information vanish, violating quantum rules, or is it encoded in the radiation? Physicists propose multiple solutions. Some suggest information escapes in the radiation. Others argue it is preserved at the event horizon in a holographic manner. Recent advances in quantum gravity, string theory, and the study of entanglement provide promising frameworks. These approaches show that even at the most extreme densities, physics remains consistent. Information is not lost. It is transformed, encoded, or redistributed. Studying these interactions informs our understanding of a universe-scale black hole. If the cosmos itself behaves like an interior of a black hole, then quantum effects would influence its evolution. Matter and energy would follow rules dictated by both gravity and quantum principles. Hawking radiation at cosmic scales could manifest subtly, affecting energy distribution and the formation of structures. The entropy of the universe, a measure of disorder, would be shaped by the geometry of space and the boundaries defined by containment. Quantum mechanics also affects the formation of stars and galaxies. Fluctuations in density, seeded at the earliest moments, grow under gravity to form clusters and filaments. These fluctuations may reflect initial quantum processes inside a contained, curved space. The resulting large-scale structure aligns with what we observe in cosmic surveys. The intersection of quantum mechanics and relativity highlights the delicate balance of forces in extreme environments. Black holes serve as laboratories, testing principles that are otherwise inaccessible. Semi-classical models, holographic approaches, and numerical simulations all explore how information, energy, and space-time interact. The results show that physics remains consistent, even under extreme conditions. Observations, such as gravitational waves from black hole mergers, provide indirect evidence. These waves encode information about mass, spin, and energy. They also carry subtle imprints of quantum behavior. Analysis of these signals informs scientists about the interplay between gravity and quantum mechanics. Theoretical work continues to explore how the interior of a black hole could evolve while preserving information. Entanglement, superposition, and quantum fluctuations all play roles in shaping dynamics. The debate over information loss drives research, pushing the limits of physics. In a universe-scale black hole, similar principles may apply. The structure, evolution, and energy distribution of the cosmos would be influenced by quantum processes at extreme densities. Fluctuations at small scales could impact large-scale expansion, galaxy formation, and the distribution of matter. The laws of physics remain consistent. Entropy increases locally, radiation carries information, and quantum effects integrate with gravitational curvature. No contradictions appear when models are carefully constructed. Physicists continue to test these ideas through mathematics, simulations, and observation. The intersection of general relativity and quantum mechanics provides constraints. Any model of a contained universe must respect these laws. Hawking radiation, entropy scaling, and the information paradox all define boundaries for what is possible. They ensure that a black hole-like cosmos is not mere metaphor, but a scientifically plausible scenario. The study of quantum effects also informs the interpretation of cosmic anomalies. Subtle variations in radiation, light paths, or energy distribution may reflect quantum processes operating on vast scales. Entanglement and fluctuations at the smallest levels propagate through gravity to influence large structures. The behavior of particles near event horizons offers a window into these effects. The results are measurable in principle, even if the scales involved are immense. By combining observations, theory, and simulations, scientists refine models of cosmic evolution. Quantum effects regulate energy, entropy, and structure formation. Hawking radiation, though weak on cosmic scales, sets limits and ensures consistency. Information is preserved, guiding the behavior of matter and light. The balance between gravity and quantum processes maintains a coherent interior. The laws of physics remain intact, even in conditions far beyond ordinary experience. The study of black holes shows that extreme density and curvature do not break physical principles. Instead, they reveal new connections. Information, energy, entropy, and geometry interact in precise ways. These interactions constrain the behavior of matter and spacetime while allowing a rich, dynamic universe to emerge. Researchers continue to explore these intersections, testing theories, simulating extreme conditions, and comparing predictions to observations. The interplay between quantum mechanics and general relativity informs not only black holes, but potentially the universe itself. Patterns in cosmic microwave background radiation, the formation of galaxies, and the evolution of structures can all be interpreted through these principles. Entropy grows, radiation carries information, and quantum fluctuations seed large-scale patterns. The interior of a black hole or a universe behaving similarly becomes a coherent, predictable, and scientifically grounded environment. Debates over information, entropy, and quantum effects drive progress in understanding extreme physics. The laws of the very small integrate with the laws of the very large, providing a framework for interpreting observations and refining models. The universe, if contained, would be governed by these principles. Time flows, space curves, energy redistributes, and matter organizes according to a combination of gravity and quantum rules. Hawking radiation, entropy scaling, and entanglement are all part of this picture. The intersection of quantum mechanics and black hole physics reveals a cosmos that is dynamic, coherent, and constrained by fundamental laws, offering a rigorous, non-speculative foundation for understanding what may lie at the largest scales of existence. Cosmologists explore multiple models to explain the universe's origin, structure, and expansion. The multiverse hypothesis suggests that our universe is one of many, each with different laws of physics. Some are similar to ours, others drastically different. Evidence for other universes is indirect, inferred from theoretical frameworks like string theory and quantum cosmology. These models propose mechanisms for universe formation, including bubble nucleation, where new regions of space emerge with their own expansion. Cyclic universe models suggest a different perspective. Instead of a single creation, the cosmos undergoes repeated expansions and contractions. Each cycle begins with a bounce, not a singularity, and ends in a slow collapse. Observations of cosmic microwave background radiation, large-scale structure and expansion rates inform these models. Data may support or challenge cyclic scenarios depending on how uniformity, energy distribution and fluctuations are interpreted. Inflationary theory is another framework. It proposes that the universe experienced an extremely rapid expansion in the first fractions of a second. This expansion explains uniformity across vast distances, the flatness of space, and the formation of structures. Quantum fluctuations during inflation seed galaxies, clusters, and filaments. Observational evidence, such as the cosmic microwave background and large-scale surveys, matches many predictions of inflation. Each of these alternative models has strengths and limitations. The multiverse is difficult to test, relying on indirect inference. Cyclic models explain some anomalies, but must reconcile entropy growth across cycles. Inflation provides elegant explanations, but raises questions about initial conditions and fine-tuning. In comparison, the black hole inside hypothesis offers a different lens. Instead of proposing multiple universes or repeated cycles, it suggests the cosmos is contained within a curved, finite region shaped by extreme gravity. Expansion, structure formation, and the flow of time occur naturally within this geometry. Observational data can be interpreted through this framework as well. Patterns in the cosmic microwave background, galaxy distributions, and expansion rates are consistent with a contained, curved space. Horizons, boundaries, and curvature are not directly visible, but their influence can be measured. Comparing predictions, all models aim to account for uniformity, large-scale structure, and observed expansion. Multiverse models explain variations across different regions. Cyclic models focus on repeated evolution. Inflation describes early rapid growth, and the black hole interior emphasizes containment and curvature. Each provides explanations for patterns observed today, but through different mechanisms. Science approaches these hypotheses with careful scrutiny. Evidence must be measurable, predictions testable, and models internally consistent. None of these theories is accepted as definitive. Observations support elements of each, yet gaps remain. This uncertainty drives research, encouraging new measurements, simulations, and theoretical development. Skepticism is a guiding principle. Extraordinary claims require extraordinary evidence. A universe inside a black hole is a radical idea, but it is grounded in mathematics, general relativity, and observations consistent with curved, finite space. Scientists remain open-minded, exploring its implications while comparing it with multiverse, cyclic, and inflationary frameworks. Each approach emphasizes different aspects of physics. The multiverse highlights quantum possibilities. Cyclic models focus on temporal patterns. Inflation emphasizes early dynamics. Black hole containment underscores the influence of extreme gravity on cosmic structure and time. Observational evidence, such as redshift surveys, gravitational lensing, and cosmic background measurements, serves as a testing ground for all these models. Each hypothesis must reproduce known features, explain anomalies, and remain consistent with physics. The black hole interior model fits within this scientific methodology. Predictions of expansion, structure formation, and energy distribution can be tested against observations. Differences may appear subtle, but they offer ways to evaluate plausibility. Comparing models also reveals conceptual contrasts. Multiverse ideas imply regions we cannot observe. Cyclic universes suggest past and future cycles. Inflation addresses initial growth. Containment suggests boundaries shaped by extreme curvature. Each perspective affects interpretation of time, space, and causality. The scientific process evaluates these perspectives objectively. Theories are refined, challenged, or rejected based on consistency with observations and mathematical rigor. A contained universe must satisfy constraints from general relativity, quantum mechanics, and thermodynamics. It must produce the patterns we measure today, from cosmic microwave background fluctuations to galaxy clustering. Models are simulated with increasing precision. Computer simulations, analytical calculations, and observational comparisons converge to test hypotheses. Even subtle deviations in expansion rates or radiation patterns provide clues about the underlying geometry. While certainty remains out of reach, the exercise clarifies what is physically possible. The black hole inside hypothesis does not conflict with established physics. It complements observational data, aligns with general relativity, and proposes a coherent framework. It differs conceptually from multiverse or cyclic ideas, but can be analyzed using the same scientific tools. Researchers remain cautious. Predictions must match reality. Anomalies must be explained. Entropy, energy distribution, and structure formation must remain consistent with known laws. This rigorous approach ensures that even speculative scenarios are scientifically grounded. Open-minded skepticism allows consideration of radical possibilities without abandoning empirical rigor. Observations continue to accumulate. Cosmic microwave background surveys, supernova data, gravitational wave detections, and galaxy catalogues provide ever more precise constraints. Each measurement refines models, tests predictions, and informs theoretical work. Contained universe models are evaluated alongside alternatives, not in isolation. Comparative study is crucial. Understanding strengths, weaknesses, and implications helps guide future research. The exercise illustrates the balance between bold ideas and careful validation. Radical concepts like a universe inside a black hole are explored within the framework of known physics. Their predictions are compared with observable phenomena and alternative explanations. The process reinforces scientific methodology. Theories are judged by consistency, predictive power, and alignment with evidence. Competing cosmological models expand the range of possibilities. Multiverse ideas highlight unobservable variation. Cyclic theories explore repeated evolution. Inflation describes rapid early expansion. Black hole containment emphasizes curvature, boundaries, and gravitational shaping. Each provides a lens for interpreting observations. None can yet claim definitive confirmation, but each offers testable predictions. This environment fosters continuous discovery. Scientists analyze data, refine simulations, and adjust models. The study of alternative explanations clarifies assumptions, highlights uncertainties, and drives improvements in theory and observation. A contained universe remains one of several plausible scenarios. It is examined alongside other models with careful attention to evidence, mathematics, and physical principles. Patterns in cosmic microwave background radiation, the distribution of galaxies, and large-scale expansion are consistent with multiple interpretations. Science proceeds by weighing possibilities, testing consequences, and seeking coherence with all known physics. The black hole inside hypothesis is one option among several. It is mathematically sound, compatible with observations, and consistent with general relativity. Yet it remains speculative in the sense that direct verification is currently impossible. Scientific skepticism ensures that it is treated critically, while open-mindedness allows exploration of its consequences. In this context, all models, multiverse, cyclic, inflation, and containment, are evaluated for consistency with known phenomena, predictive power, and mathematical integrity. Comparative analysis reveals how geometry, gravity, and quantum effects shape the evolution of the cosmos. It demonstrates that even radical ideas can be rigorously examined within science, offering insights into the fundamental structure and behavior of the universe. Assuming that the universe might be contained inside a black hole changes the way scientists look at everything. Distances, structures, and motions take on new meaning. The vastness of space may feel infinite, yet the geometry could curve back on itself. Boundaries may exist that we cannot see directly. Horizons, defined not by visible walls, but by the curvature of space-time, could shape the flow of matter, light, and energy. Observers measure motion and expansion with this perspective in mind. Galaxies move away from each other, redshifts increase, and structures form along predictable patterns. But if space is curved and contained, these patterns are not random. They follow the rules dictated by a large-scale interior, geometry. Gravitational waves offer a new way to test these ideas. Ripples in space-time, generated by colliding black holes or neutron stars, travel vast distances. They carry information about the mass, spin, and distribution of matter. Scientists detect these waves with instruments like LIGO and Virgo, analyzing their signals to learn about the underlying curvature of space. Patterns in wave propagation could hint at large-scale containment. Subtle deviations, distortions, or timing anomalies might reflect a curved interior rather than open space. Cosmic mapping is another approach. Large surveys chart millions of galaxies, measuring positions, velocities, and distributions. These maps reveal filaments, clusters, and voids. When interpreted through the lens of a black hole interior, these structures align with the geometry of a finite yet unbounded space. The distribution of matter follows the rules of gravity acting in curved space. Simulations complement observation. Computers model billions of years of evolution, tracking galaxies, dark matter, and radiation. By adjusting parameters for curvature, expansion, and boundaries, scientists explore whether observed structures emerge naturally. When simulations replicate patterns seen in reality, the models gain credibility. Even small anomalies in the cosmic microwave background or large-scale flows can be tested in these frameworks. Limitations remain. Direct measurement of global curvature or boundaries is beyond current technology. The horizon of a universe-scale black hole cannot be reached or imaged directly. Observers inside cannot measure distances in ways that reveal the entire structure. Yet indirect methods provide insight. Gravitational lensing, light travel time, redshifts, and radiation patterns all offer clues. Precision instruments are key. Improved telescopes, detectors, and satellites allow more detailed measurements of cosmic radiation, galaxy positions, and motion. As sensitivity increases, subtle effects predicted by a contained geometry may become detectable. Future experiments may focus on variations in gravitational wave propagation across vast distances. Signals from multiple sources could be analyzed collectively to detect patterns consistent with curvature. Likewise, mapping of cosmic background radiation at higher resolution could reveal correlations or anisotropies that indicate boundaries. Observational strategies continue to evolve. Scientists combine data from multiple sources, cross-referencing galaxy surveys, radiation measurements, and gravitational wave events. Each dataset constrains models, ruling out some possibilities and refining others. The black hole interior hypothesis can be tested alongside other cosmological scenarios, such as inflation or cyclic models. Differences in predictions, such as the precise curvature of space, the distribution of radiation fluctuations, or the flow of expansion, provide measurable benchmarks. Simulations play a crucial role. By modeling a contained universe under general relativity, including quantum effects where relevant, researchers explore how matter, energy, and light evolve over billions of years. Comparing results with observation shows whether the hypothesis is plausible. Success depends on matching both large-scale patterns and small-scale anomalies. Despite progress, challenges persist. Cosmic scales are immense, and signals are faint. Observations are limited by instrument sensitivity, noise, and the distance of sources. Cosmic variance, the statistical uncertainty due to observing only one universe, complicates interpretation. Even so, methods continue to improve. The combination of theory, simulation, and measurement allows scientists to probe the universe in ways previously impossible. Viewing the cosmos as a potential black hole interior shifts perspective on its size and fate. Expansion may eventually approach a limit defined by geometry. Structures may form and evolve under constraints imposed by containment. Light travels along curved paths, horizons exist, and time may flow differently in different regions. This framework provides a new lens for interpreting observed phenomena, from galaxy distributions to cosmic microwave background fluctuations. Each observation becomes a test of curvature and containment. The universe is no longer simply vast and open. It is structured, shaped by the rules of extreme gravity on a cosmic scale. This perspective does not conflict with known physics. General relativity, quantum mechanics, and thermodynamics continue to apply. Predictions remain consistent with observed structures, radiation, and expansion. What changes is the interpretation, the way scientists connect data to the underlying geometry. Opportunities for future research are immense. As instruments improve, as simulations increase in complexity, and as data accumulate, subtle effects predicted by a contained geometry may be measured. Light paths, redshift patterns, gravitational wave propagation, and radiation distribution can all reveal hidden curvature. Horizons, while invisible, influence the observable universe in measurable ways. Scientists are beginning to probe these effects systematically. Each new measurement refines understanding. Constraints on expansion, curvature, and structure formation improve. Patterns in radiation and matter reveal how the interior geometry influences local and global behavior. Even small deviations from standard models can provide crucial evidence. Observing the universe differently means recognizing that familiar phenomena, galaxy motion, radiation, large-scale structure, may reflect underlying curvature and containment. Every photon, every gravitational wave, and every galaxy acts as a tracer, providing information about the geometry of space. The potential for discovery is vast. Researchers aim to quantify curvature, test predictions, and explore the interplay of gravity, quantum effects, and cosmic expansion. Each result narrows the range of possibilities, bringing clarity to questions about size, boundaries, and evolution. The horizon of a universe-scale black hole, while unreachable, influences observable physics. Its existence is inferred from patterns, from structure, from the behavior of light and matter. Observational strategies continue to improve, combining survey data, precision instruments, and advanced simulations. Limitations remain, but each step increases confidence in interpretations. By observing differently, scientists probe the universe not as an open, unbounded expanse, but as a structured, curved, contained region. The flow of time, the path of light, and the evolution of matter are all shaped by underlying geometry. Expansion, structure formation, and cosmic background patterns are influenced by curvature and horizons. This approach offers a new framework for understanding phenomena that might otherwise appear puzzling. The study of a black hole-like universe combines observation, simulation, and theory. Each informs the other, building a coherent picture of how large-scale structures evolve under extreme gravity. Horizons, curvature, and time dilation all play measurable roles. Observers inside measure distances, radiation, and velocities, all influenced by geometry. The interplay between measurement and model allows scientists to test the hypothesis rigorously. While certainty is elusive, the approach offers a method to explore the cosmos systematically. Viewing the universe differently does not discard known physics. It applies familiar principles to a novel scale. The potential of detection, refinement, and comparison ensures that observational science remains rigorous and grounded. Every new dataset, whether from gravitational waves, galaxy surveys, or radiation mapping, contributes to understanding. Simulations bridge gaps between theory and observation, predicting patterns that can be sought in data. The process is iterative, methodical, and empirical, maintaining a clear connection to measurable phenomena. In this way, the black hole interior hypothesis remains scientifically viable while encouraging innovative observational strategies. The universe is examined not as an abstract concept, but as a system governed by gravity, quantum effects, and geometry. Horizons influence observations, curvature shapes structures, and time flows along predictable paths. Observing differently is both a challenge and an opportunity. It allows the probing of boundaries, the testing of predictions, and the refinement of models. Current limitations are technical and conceptual, yet future possibilities are vast. New instruments, improved simulations, and refined theories promise deeper insight into the true nature of space, time, and cosmic structure. Each observation becomes part of a larger pattern, revealing the subtle effects of curvature, containment, and extreme gravity on the evolution of the universe. This perspective transforms measurement into discovery, allowing scientists to explore a universe that may be finite yet unbounded, structured yet expansive, visible yet shaped by horizons we cannot cross. After exploring the possibilities, patterns, and physics, the universe appears in a new light. Vastness no longer implies emptiness or infinity. Containment may shape everything we see, from the motion of galaxies to the flow of time itself. Observations of light, radiation, and matter provide hints of structure, but the full shape remains hidden. Horizons influence what is visible, boundaries constrain what can be measured, and curvature guides the paths of energy and matter. Space is not simply a stage. It is dynamic, shaped by gravity, mass, and quantum processes. The cosmos unfolds along rules that are precise yet subtle. In this framework, human existence is both small and significant. Our planet is a tiny observer, a point within a vast system governed by forces beyond everyday experience. Every measurement, every observation contributes to understanding, yet remains bounded by perspective. Stars rise and fall, galaxies rotate, and cosmic radiation flows, all guided by the underlying geometry. We experience time locally, measure distances, and trace light across billions of years, all while embedded in a system that may curve back upon itself. The flow of energy and information continues relentlessly. Entropy increases, radiation travels, and structures evolve according to laws that are consistent and measurable. Our instruments detect these effects, from subtle shifts in galaxy positions to faint variations in the cosmic microwave background. Gravitational waves ripple through space, carrying information about events we cannot otherwise perceive. Through observation and simulation, scientists map the consequences of curvature and containment. The perspective shifts from seeing the universe as infinite to seeing it as vast yet structured. Boundaries are implied, not observed directly, and horizons define limits without physical walls. Light and matter follow paths shaped by this curvature, revealing the invisible framework that guides the cosmos. Quantum effects and gravity intersect to regulate energy, entropy, and information. Hawking radiation, entanglement, and fluctuations play roles across scales, from the smallest particles to the largest structures. Even as galaxies form and stars burn, the influence of extreme gravity shapes the evolution of the system. Patterns in radiation, distributions of matter, and the motion of galaxies all reflect underlying geometry. Observers record these patterns, interpret them, and refine theoretical models. The work is ongoing. Uncertainty remains, but inquiry continues. Measurements improve, simulations become more precise, and understanding deepens. Each observation provides a small piece of a vast puzzle, gradually revealing the structure of a universe that may be contained, curved, and shaped by extreme physics. Humanity occupies a brief instant within this immense framework. Life on Earth, the rise of consciousness, and the ability to measure and reason are temporary features in geological and cosmic timescales. Yet they allow the tracing of patterns, the interpretation of signals, and the formulation of theories. We see stars as they were millions or billions of years ago. Radiation carries information across unimaginable distances. Our perspective is local, but our reach extends through careful observation and theory. Considering the universe as potentially contained brings perspective to scale and duration. Expansion, motion, and radiation occur within limits that may be defined by geometry. Observers inside measure events with local rules, yet the global shape constrains what is possible. Curvature, entropy, and energy flow guide the cosmos. Space and time are intertwined, flowing together along paths dictated by mass and geometry. Horizons are present but intangible, defining what can be observed without preventing the evolution of the interior. Expansion continues, structures form, and time progresses, all in accordance with known physics. Observational methods, from cosmic mapping to gravitational wave detection, continue to refine understanding. Each measurement is a probe, each simulation a test of theory. Unseen boundaries influence what is visible, shaping the patterns we detect. Large-scale structure, radiation distributions, and cosmic flows all carry information about the underlying geometry. As knowledge accumulates, perspective deepens. The universe is both familiar and strange. Stars, galaxies, and radiation behave according to predictable laws, yet the larger framework may curve, contain, and guide these phenomena in ways invisible to the naked eye. Space is dynamic, time flows differently depending on location, and curvature subtly affects every measurement. This perspective underscores the connectedness of all scales, from quantum fluctuations to cosmic filaments. The laws of physics operate seamlessly across these scales, integrating gravity, quantum effects, and thermodynamics. Energy moves, information propagates, and matter organizes consistently. Observers within the system gain insight through careful study, revealing patterns that reflect the geometry and dynamics of the cosmos. Humanity's role is small but meaningful. The ability to detect radiation, measure motion, and interpret signals is unique in cosmic history. Each discovery builds understanding, providing glimpses of a structure far beyond direct perception. Knowledge grows incrementally, guided by rigorous observation, simulation, and theory. Curvature, horizons, and quantum effects shape the universe quietly yet powerfully. Observers trace light paths, detect gravitational waves, and record cosmic radiation, gradually piecing together the hidden framework. Expansion proceeds, matter organizes, and energy flows, all within the constraints imposed by geometry and gravity. The universe continues to evolve, and understanding evolves alongside it. Science progresses methodically, testing hypotheses, refining models, and interpreting data. Each insight deepens comprehension of a cosmos that may be finite, curved, and bound by extreme physics. Observations, simulations, and theoretical analysis combine to reveal structure without needing to cross boundaries or directly access horizons. Time, space, and energy flow in ways that are measurable and predictable, even when shaped by subtle curvature. Considering this possibility transforms perspective. What seemed infinite may be finite. What seemed unstructured may follow hidden rules. What seemed remote may carry information about the entire system. Patterns in galaxies, radiation, and motion reflect underlying constraints. Entropy increases, radiation propagates, and matter evolves according to laws that operate consistently throughout the cosmos. The process of observation, analysis, and modeling continues, each step revealing more about how the universe functions. Containment, curvature, and extreme gravity are not obstacles. They are the framework within which cosmic processes occur. Understanding deepens as instruments improve, simulations advance, and theories refine. Observers gain insight into the relationship between local events and global structure. Light travels along curved paths, time flows differently depending on location, and energy moves according to predictable rules. Horizons and boundaries influence patterns without appearing as physical barriers. Humanity, fleeting and small, perceives and interprets. Stars rise and fall, galaxies rotate, radiation flows, and cosmic expansion continues. The universe operates according to laws that are both subtle and powerful, guiding the evolution of matter, energy, and information. Observers detect, measure, and model. Each step increases comprehension while remaining aware of the vast unknown. The perspective gained is contemplative and expansive. We are part of a system shaped by forces beyond direct perception. Space curves, time flows, and gravity guides all motion. Light, radiation, and matter carry information about structure and dynamics. The universe may be contained, curved, and shaped by physics at extreme scales, yet within it, evolution proceeds with coherence and consistency. Reflecting on this, the cosmos appears as a dynamic, structured, and interconnected system. Observers occupy a brief instant, measuring patterns, testing theories, and interpreting signals. Expansion, radiation, and motion continue under the influence of gravity, curvature, and quantum processes. Horizons define what can be seen. Time flows locally, yet is shaped by large-scale structure. Patterns emerge, signals propagate, and energy moves according to consistent laws. The exploration of these principles encourages careful observation, methodical analysis, and thoughtful reflection. Understanding grows, incrementally, revealing how large-scale structure, cosmic radiation, and energy distribution all reflect underlying curvature and containment. While definitive answers remain beyond reach, the process of inquiry enriches perspective, highlighting both humanity's smallness and its capacity for insight. The universe continues, vast and structured, evolving according to known laws, while observers trace its patterns, study its signals, and reflect on their place within it. In this contemplation, the cosmos is at once immense and intimate, distant yet perceptible, mysterious yet governed by precise principles. It is a system of subtle rules and measurable effects, where expansion, curvature, time, and energy interact in ways that remain both observable and profound. Containment, horizons, and curvature guide motion and structure. Observers record, interpret, and model, deepening understanding while acknowledging limits. The universe flows, evolves, and expands, and humanity follows in quiet observation, tracing patterns, measuring signals, and reflecting on its position within this grand, dynamic system.